It's 12 o'clock. I'm going to begin. Today I'll be talking about fluid statics, or hydrodynamic, or hydrostatics is what it's otherwise referred to. In the previous lessons we were talking about water when it flows and how pressure can change. And the main equation that we kept using over and over again was Bernoulli's equation. And then we talked about different types of retarding forces, like the drag force, the coefficient of viscosity force, and so on. So those was everything about the fluid dynamics that I wanted to talk about. There's a lot more that you could touch upon, but not for the sake of this class. Now we're going to move on to fluid dynamics, to fluid statics. Usually it's the other way around. You talk about fluid statics first because you learn about pressure, and then you can talk about fluid dynamics. But I kind of feel like if I talked about that, then it gets too boring. So now you'll have somewhat of an understanding. We're talking about fluids that are stationary. Let's say we have some pool or something right here. This box represents a body of water, and we're going to put a little rectangle inside there, and we're just going to drop it. And then in here, we want to ask ourselves, what is the pressure? C-Dubs is here. C-Dubs making an appearance. That's what celebrities do. They make appearances. Okay. So, anyways, if you've ever been in a swimming pool and you go like to the bottom of the swimming pool, you feel some sort of heaviness. You feel a pressure. And that's kind of what we're going to be talking about. When you drop an object into some body of water, as it falls down, what is the pressure over there? Well, we have an equation for pressure. Pressure is equal to the force multiplied by the, force divided by the area. So pressure equals force divided by the area. And the area we're talking about is the cross section, not the height distance right here, but the cross section, so slices of this object that we're dropping in there. So we could write this as the force divided by the area, which is A times B. Okay, so that's what we have for pressure so far. Something else we can say is that the force is equal to, what do we want to say that the force is equal to? The weight, mg. So the force that's pushing this object down is the weight of its mass, whatever. And we can rewrite that as the density multiplied by the volume multiplied by g, because mass is the density times the volume. And so now we have an equation, density volume times g over A multiplied by B. And the volume is the volume of this object, so it would be A times B times H. So that's equal to the density multiplied by the volume, which is A times B times H. It's a rectangle, or a prism, whatever you want to call it, times G, all divided by AB. And so the A's cancel out, the B's cancel out, and we have an equation for pressure. Pressure would equal the density of the fluid multiplied by the height multiplied by G. So we're going to rewrite that. I'm going to put the G in the front. But also, I want to know the pressure for any point, not just like the distance from here to here, but for any object that's falling. So it's falling at delta Y here. So the equation that we're going to have for pressure instead is going to be rho times G. And instead of putting the H there, we're going to put for any distance Y. And that is the equation for pressure for an object that's falling down, rho G Y. Okay? For example, let's say that we had this object right here, and we wanted to know maybe the depth of this distance right here was 2.4 meters. So if you had 2.4 meters here and we plugged it into our equation here, what would we end up with? Well, we would end up with the density of water, which is 1,000 kilograms per meter cubed, multiplied by G, 9.8 meters per second, squared, multiplied by the depth. So this could be like the bottom of a swimming pool maybe. And so 2.4 meters, that's a pretty deep swimming pool. 2.4 meters. And what do you end up for pressure? Pressure, when you multiply all those together, is going to equal 23,520 pascals. So this is going to give you the units of newtons per meter squared. A newton per meter squared is another unit for Pascal, PA. Okay, so you got 23,520 Pascal. What does that mean? Like, is that a lot of pressure? Is that pressure all the way at the bottom of that pool a lot? Well, we can compare it to the atmospheric pressure. So we could say the pressure at the bottom of the pool divided by the atmospheric pressure. And we can see how much it's actually going to be. So the pressure at the bottom is 23,520 Pascal. And atmospheric pressure is 101,300 Pascal. So the pascals cancel out, and you end up with 0.23, or 23%. So at the bottom of the pool, you are going to experience 23% atmospheric pressure. And this is kind of going to lead us to the next thing that we're going to talk about, which is the gauge pressure versus the total pressure. So when I say 23% of atmospheric pressure, does that make sense if I say 23% atmospheric pressure? Because right now I'm not in the pool. If I'm not in the pool, I experience this much pressure. So when I'm in the pool, I only experience 23% pressure. That doesn't make any sense because I know I feel more pressure. So what I'm really experiencing is not only the pressure from the atmosphere, but in addition to that, I'm going to experience an additional 23% atmospheric pressure. And that's what we call the total pressure. So let's discuss the difference between gauge and total pressure. I'm going to erase this. And we'll bring this up here. So we've got the gauge pressure versus the total pressure. Now, at the top of whatever pool or something that you have atmospheric pressure. And then what I want to know is what's the pressure down here? So to find the pressure right there, we just use our equation. We have the distance, which is going to be 4 meters. We have, and that's kind of all we need, isn't it? So the pressure at the bottom right here is equal to rho g y. And so it's going to be 1,000 times 9.8 times 4 meters. And when you do that, you're going to end up with 39,200 Pascal. Okay, so what is this value right here? This value is really just the pressure due to the weight of the water only. So this is the pressure of the weight of the water only. So from here to here, this is the pressure of the water by itself. If we wanted to know the total pressure, if we wanted to know what the total pressure was, P total, then what we have to do is we have to take the atmospheric pressure and add to it this pressure right here. And there's a name for this pressure by itself, the weight of the water only. That's called the gauge pressure. P gauge. Oops, G U-A-G-A-U-G-E. So that's the gauge pressure. So we're going to add to it the pressure due to the gauge. And so that's our equation right there. So atmospheric pressure is 101,000 roughly Pascal plus this pressure, which is 39,000. When you add those two together, you will get a total pressure of 140,000 140,500 newtons or Pascal, not Newton per meter squared. So that's the total pressure. Okay, so typically when you look at devices that measure pressure, they tell you the gauge pressure. They don't tell you what the total pressure is. Why would we not want to know what the total pressure is? But it's more important to know this value right here. Why don't we care about this, but care about this? And that's because we don't really experience the atmospheric pressure. Like, it's on us, but we don't feel it. Like, there's no feeling of it because we're so used to it. It would be the equivalent of like our weight. Like, I don't feel my weight, maybe if I get a little heavier, but if I eat a little of those donuts right there. But let's say like I can't experience my own weight, right? I don't feel it. The only time I'm going to experience heavier is if somebody like wanted a piggyback on me. So they're adding something to my regular weight. So my original weight I don't feel, but when you add something to it, then I feel it. And that's what the gauge pressure is. It's what I'm going to be, the additional stuff that's going to change what I feel like. And so we could draw that with the swimming pool example. So let's say this is the base of a swimming pool here. Over here is just your atmospheric pressure. You don't really feel any pressure at the top of the pool right here. But when you go down into the pool, if you ever like sink to the bottom right here of the pool, then you actually feel, this is the definition of the feel pressure here. So you're definitely going to feel pressure here. You're not going to feel so much pressure here because you're used to it here. And that difference in the feeling from here to here is what we define as the gauge pressure. Okay? Another example that we could use for gauge pressure to actually understand it a little bit better is with tires. Tires are measured in kilopascals, but we look at it in terms of tires as well. So here's a tire. Okay, and let's say you had like a little bit of a flat tire and you wanted to measure its pressure. So you put in a little device that measures its pressure. The device looks something like this. It's a little tool, and then this tool will go up and down depending on the pressure. So what's actually happening here? Well, there's pressure that's going inwards. There's a pressure that you're going to experience inwards, and that's the pressure of the atmosphere. And then inside the tire, there's going to be a pressure pushing back on it. So there's a hole here, there's a hole here. The pressure pushing back on it, well, what's that going to equal? That's going to equal the total pressure. Over here, this is going to be P total. Total. So you have a pressure going this way, you have a pressure going that way. What's the total pressure going to be when you add them together? Just like when you add forces together, what's the total pressure going to be? Well, it's going to be P total. That's the inward pressure pushing out minus the atmospheric pressure, which is pushing in the opposite direction. And we know that P total is just the atmospheric pressure, ATM, minus the gauge pressure. And then we have this atmospheric pressure right here, ATM. And so the atmospheric pressures cancel out, and the pressure that this object is reading is just the gauge. So it's the difference of the atmospheric pressure. That's what we define as the gauge pressure, the difference in the total pressures. So that's why we look at gauge pressure and not the atmospheric pressure, because we already experience it everywhere. Inside the tire, not only do you have the atmospheric pressure, but you also have the air that's been built up that you put in there. and that's pushing out. And that's what the gauge is. Okay? So there is gauge pressure. The next thing, since we're talking about pressure here, is what about the pressure in a tank on the walls? So if you ever have a fish tank or a pool, when you fill it up, each side of the wall is going to experience a force that's pushing it out. And if you try to put maybe something with a lot of density in there, then the walls will implode. They'll go break, or the glass will break, is what I should say. So in a swimming pool, let's look at one wall on the swimming pool. So here's our swimming pool wall. These are the other sides of the swimming pool. We don't really care about those sides. Here's my swimming pool. I'm just looking at one side of the swimming pool. And the swimming pool has a height h. And a length of one side is L. Okay. And we've got some fluid. We've got it filled to the brim. So let's fill our pool to the brim. And this is just one side of the pool here. And I want to know the force that's pushing on this side of the wall. So there's going to be a force that's pushing on equal sides of the walls here. Not an equal amount of force. It's going to depend on the cross-sectional area right here, or the surface area of this wall. And then this surface area might be different than this one right here. So you're going to experience different forces. I just want to know what the force against this wall right here is. And the thing is that the force isn't going to be a constant value. Why is the force not going to be a constant value? Because the pressure here, we could say P1, is going to be different than the pressure here. You know, the further that you go down inside a swimming pool, that's what we just talked about, the pressures are going to be different. And if the pressures are going to be different here, then the force that's pushing against this side of the wall right here versus this length of the wall right here is going to be different. So force, or I guess pressure, is going to change with respect to y. So pressure is changing as a function of y. So how are we going to write this? Well, we know that pressure is equal to the force over area. And so I'm going to rewrite this as the force because that's what we're trying to find. The force against this wall is going to equal the pressure as a function of y, because the pressure is changing with y, multiplied by the area. And the problem is that because this is changing with y, then each of these lines right here is going to be a little bit different. So what we need to do is actually take incremental values. So what I'm going to do is look at a little bit of the surface area, let's say right here. And so this distance is y, and the thickness of this little bit right here, the thickness of that is dy. So we need to figure out what the area of this little line is as well. We know that the thickness is dy, and the length is the constant. So if I look at this line, or a line right here, or a line right there, they're going to have the same length. So we need to rewrite some of our variables here. The first thing is we're not looking at area anymore, we're looking at dA. And this is going to become a little bit of the force. So a little bit of force is only along this line. Then you have another bit of force. So if we want the total force, it's going to equal the integral of dF. And that's going to equal the integral of the density of the pressure as a function of y times dA. And so what is the pressure as a function of y? We already solved that. It's rho g y. So that's what I'm going to replace with that term. How about dA? dA is just the area of this line right here. And that's going to be like a rectangle. So it's going to be the length, which doesn't change, times the dy, the thickness. Length times what height, or length times width, whatever you want to call it. So we have density, and we have this. We can replace it into our integral here. And we get that the force is equal to the integral of rho g y L dy. And we're evaluating it from a height. Let's see, did I give a height yet? No, we didn't get a height yet. So we'll just call from y equals 0 to y equals h, because h is the total height of the pool. And so what do we end up with? We can take out some constants. The density gets out, g comes out, L comes out, and we have the integral from 0 to h of y dy. And that's just equal to, do I have some space down here? Yeah, I do. That's going to equal 1/2 rho g L H. And so that is the force. That is going to be the force 1/2 rho g L H squared. I forget the squared term because you got to square this. 1/2 rho g L H squared, and that's the force against one side of the pool, or one of the walls against the pool right there. Let's put some numbers in and actually see what happens here. So the length, we'll say L is equal to 10 meters. That's a pretty long pool. Maybe it's an Olympic-sized pool. H is equal to 2.8 meters. Yeah, so maybe it is an Olympic pool. 2.8 meters. And that's all we need to know. We know density of water is 1,000 kilograms per meter cubed. So if I plug those numbers into here, what am I going to end up with? I'm going to end up with 384,000. The force against the wall is going to equal 384,160 newtons. So that's the force that's going to be against the wall. Now, there is another way to do this, but it's going to depend on whether your density is uniform. If your density is not uniform, you can't use this other way. So in this case, it's just water all the way through here, so we're good. But let's say you had a swimming pool with water and oil. As you go down, then the pressures there's going to be two different pressures, so you can't use this other way. The other way of doing it is like this. We could just look at the middle and find the average pressure. So the average pressure, AVG, is equal to the density times gravity times H divided by 2. That's the average pressure here. And so what can we do with that? Well, force is equal to the average pressure. So the average force, I guess we could say, I don't know, let's just call it regular force, is equal to AVG multiplied by the area, A. Okay, so this would be the area of the wall, the surface area of the wall. And that's equal to rho g h over 2. And the area is the length times the height. So length times h. And you end up with rho g h squared L divided by 2, which is the same result we got using integration. Okay. So that's that. And the last thing I'm going to talk about now is the hydraulic lift. So if you ever have a car and your tire, you get a flat, that you have to lift your tire up, that requires a hydraulic system, a hydraulic lift. Something else, elevators, if you go up and down an elevator, they're probably using, or they're not probably, they are using hydraulic lifts. Where else would they use hydraulic lifts? So to crush things, they use a hydraulic lift system. So it's an important thing that we use every day. And we get the hydraulic system from a principle called Pascal's Principle. So P-A-S-C-A-L, Pascal's Principle. So what is Pascal's Principle? Well, if you've got, let's say, a closed system here we've got a closed system here where you've got a little bit of opening here. And how do I want to draw this? Do I want to draw it like that? I don't think I need this part. Yeah, I don't need that part. So I've got this fluid inside of here, like so. So there's an opening here, there's an opening, a wider opening there. And this is a three-dimensional object, by the way. So you've got some fluid here, and it's going to line up nicely over here. And what you do is you put two pistons. A piston is a device that you can push in or out. So we'll have a piston right here, and we'll have a piston right here. Okay? So there's one piston, there's the other piston right there. And so you're going to apply a force this way, which we don't know yet what it is, but I do know the area of this. The area of this A1 is going to equal 2 inches squared. So that's the area of this little piston right here. We have another piston right here, and the area 2 of that piston is going to equal 100 inches squared. And let's say on top of this piston, you've got this really chubby baby. What chubby baby should I draw? We have a chubby baby. Here's our little chubby baby. It's a cute little baby. And the weight of this baby right here that's pushing down on it is equal to something small, 2,000 pounds. Okay? So that's the force experienced by that baby right there. And we want to know how much pressure I need to push on this one, this piston right here, to make this baby go up. And this is in engineering, we'll call it a mechanical advantage, because as long as you have a tinier distance here, you can generate a much greater force than over here. So if you wanted to lift something heavy up, if you set up an apparatus like this, you'll be able to lift it up. And it goes by Pascal's principle, this idea where the pressure is equal everywhere in enclosed fluid. So the pressure here, 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 anywhere along this enclosed fluid that's not moving has to be the same. That's the whole idea of Pascal's principle. And so the pressure at 1 has to equal the pressure at 2. That's Pascal's principle. So pressure is defined as the force 1 divided by A1, and that's going to equal force 2 divided by A2. Okay? And we could solve for force 1. Force 1 is going to equal force 2 multiplied by the ratio of A1 divided by A2. And then from here, this is pretty intuitive. You can see that if this is bigger than this one right here, you're going to get a large force generated. If this is smaller than this one right here, then you're going to get a smaller force that's required. So if we plug in our numbers here, we have the force on 2, which is the 2,000 pounds. And we multiply it by the area of 1, which is 2 inches divided by 100 inches squared. We will get that the force required to push down on this one to lift this one up, this person would be 40 pounds. So instead of having to put 2,000 pounds this way to get 2,000 pounds up this way, you only need to put 40 pounds down this way to get 2,000 pounds up that way. And that's how you get a car jack or any sort of hydraulic lift system, is because of this principle right here. Okay? But with, let's say, an elevator and even a car jack, they usually have some compression of air. So instead of you pushing down on this, they have what's called a compressor, and it pushes air down this way, and that force of air that's being pushed down this way will force this thing to go up that way. So if you see a machine that crushes things, you'll hear a machine that goes, that's something that pushes air into here. You've probably seen those in like your bike tanks, or like if you go to a gas station and you need to fill up your tires, you'll hear that machine that goes, that's pumping air. And that's what we'll be doing something right here as well. Okay, so that's it for today. I am done. Talked about a few things. and we'll continue on Monday. So until then, adios. Whoop.